In exercise 2, we want to find a differential equation for the survival probability. We are given a Cramér-Lundberg process where the initial capital is U, we have a premium rate C, we assume that the claim size distributions are IID and follow the distribution G, and the arrival rate is lambda. Note that since the Cramér-Lundberg process is built on the assumption that the claim number process is a Poisson process, then it follows that with an arrival rate lambda, the first arrival time will be exponentially distributed with parameter lambda. Also, we will use psi of u to denote ruin probability, and we will use delta of u to denote 1 minus the ruin probability. So we shall call this the survival probability. In A, we are asked to consider a small h and show that, or explain why it holds that when we consider the probability of survival with initial capital U minus CH, then this probability is given by e to the minus lambda h multiplied by the probability of survival with initial capital U plus some rather advanced, complicated double integral that looks like this. Where we integrate over the probability of survival, where the initial capital is u minus c h minus t minus y, and integrate with respect to the distribution of y, and then, well, as we will note just in a second, the distribution of the first arrival time. Now this is what we call the perturbation argument, and typically when we do these arguments we consider different cases where we will look at what happens if the claim number is 0 or the number of claims is 1, or if it's greater than 1. In this case, that is not what we will consider. As I mentioned in the passing a few seconds ago, we actually have here an integral with respect to the distribution of the first arrival time, where we look at arrival times from 0 to h. And what we have here is the probability of the first arrival time being strictly greater than h. So something is kind of telling me, at least, that what we look at here is different cases for the value of the first arrival time. There are different ways we can write this up formally. I will show you 2 different ways. None of them are strictly rigorous, but both will work in an exam setting, and both also work in the scope of this course. So the first way to argue is, well, at time if we consider what happens at time h minimum first arrival, we have 2 cases. The first case is if the first arrival time has not occurred yet. So in this case, what do we have? Then we just have that if we want to consider the probability of survival given initial capital U minus CH, then it is the same as, well, at time h, there has been no arrivals yet. So it corresponds to starting a new Cramer-Lundberg process at time h, where the initial capital no longer is u minus ch, but also includes the premium that we have earned in the time interval (0 to h). Okay, so that is the case if t1 is greater than h. Now, what if the first arrival is here before time h? Well, then the probability of survival would in that case be a bit different, right? Because then we only have information up until the time when t1 occurs, and at time t1 we will start a Cramer-Lundberg process anew, where the initial capital will then be u minus ch plus c multiplied by t1. This is the amount that we have earned in premium from time 0 to t1. And apart from that, we also have to pay out a claim, the first claim which arrives at time t1, which is y1. And there are a few things we note here. One is that ct1 is the premium earned in the time interval 0 to t1. However, the other thing that we should probably note is that this only makes sense to think about if y1 doesn't ruin us. So we require that y1 should not exceed the amount of capital we have at the time when the claim size y1 is paid out. Now, gathering all of these observations into one equation, what we see is this. So if I have the case where the first arrival comes after time h, well, then what we are considering at that time will be the probability of survival given an initial capital U, because these two will just cancel. And then I multiply by the probability that t1 is greater than h. Now, if the first arrival comes before time h, then the probability of survival will be one that we calculate upon this initial capital. Now we have to sum over all the different cases that can occur for t1 and y1. And when I say sum over, that's just heuristic language for integrating with respect to first the distribution of t1, then the distribution of y1 over all the different values t and y that they can take. So first of all, the values that t1 can take will range from 0 to h. So 0 to h. And the values that the claim sizes may take for this to make sense, well, they range from 0 and all the way up to u minus ch, and then plus c multiplied by whatever value this t1 has, which inside the integral is just t. In the case where we have that the claim size is y and the first claim arrival comes at time t, we then have that, well, then at that time point a new Cramer-Lundberg process starts with initial capital U minus c multiplied by h minus t multiplied by y. And then we integrate with respect to the distribution of y, and we just continue on to the next line here with respect to the distribution of T1. And if we just finish our calculation here, then we see that this is delta u multiplied by the probability that the first arrival is greater than h. Well, that is e to the minus lambda h. And then plus the integral from 0 to h, integral from u minus, from 0 to u minus ch minus t. And what we integrate is this probability that I just told you guys about here. And we actually see that we get the result that we wanted to show. So that is one way we can argue for this. And I actually think that this is the standard perturbation argument. Some of you guys might want to be able to write things up a bit more probability theoretically, maybe. And in that case, I can also recommend writing the probability, the survival, probability of survival as well using p's. The probability of, let's just write it in shorthand, of survival given an initial capital of u minus ch, together with the fact that the first arrival arrives after time h, plus the probability of survival with initial capital U minus ch, together with the fact that t1 is smaller than or equal to h. Then you can write up the second integral by doing a double expectation of the second term. So just take the expectation conditioned on y1, and then expectation conditioned on t1 down here. And up here you can try to split out the t1 greater than h probability. So you can also try to do it this way. However, I actually recommend this kind of argumentation for an exam solution, because this is the way Jeffrey argues, and this is also the way Schmidtly argues.